All right, so as we talked about last time, we need more models of bonding and structure to figure out the properties of our coordination compounds with our transition metals. So think back to Chem 101. If we have a free metal just by itself, it's got some d orbitals. So we'll call these Nd, and there's 5 of them. And one thing you did in Gen Chem is basically say that these 5 orbitals are all the same energy. But something's all the same energy. This is known as degenerate. Cool. So let's take a look at these 5 orbitals. So here's a picture of them. You can see 4 of them are kind of these 4-leaf clovers, and then one's kind of this dumbbell with this sphere inside. So what we do in crystal field theory is we take a look at the orbitals, and then we pretend that ligands are coming at them. The ligands are going to be coming at them. And here we're going to take a look at an octahedral setup. So if we're thinking about an octahedral setup, we've got a ligand on the top, on the bottom, the sides, and coming in and out of the board. So basically we've got all of them, or we've got a ligand on each axis. And so remember that ligands donate electrons, and remember that these orbitals also have electrons in them. So electrons and electrons are going to repel one another. And so when they get close together, that's going to cause a higher energy. And when they're not as close together, that's going to be a lower energy. So if we think about this one right here, these ligands are coming and they're hitting this orbital right on the face, right? So that orbital is going to go up in energy. And same thing with this one, right? The ligands coming from the top and the bottom, so the ligands are going to make direct contact with these orbitals, causing an increase in energy. Whereas these other ones, if you look at these other orbitals, the ligand's not going to come in direct contact with any of them. And so that'll result in a lower energy. And so you don't really have to know too much about the specifics there. Just understand that it's these ligands interacting with these orbitals that's going to remove this degeneracy. All right, so we're going to go from a situation in which we have 5 degenerate d orbitals. Some of them are going to go up in energy, and some of them are going to go down in energy. So this will be the YZ, the XZ, and the XY. You don't have to know that. Just know the overall look of what this looks like. And then up here is Z squared, and then this is X squared minus Y squared. So this is the crystal field theory kind of energy diagram for an octahedral setup. So we can see some of our orbitals are still degenerate, some of them are not, and so there's an energy gap here. And so this energy gap is going to determine many of the properties that we see. And there's many ways to control this energy gap, or there's many things that it depends on. So it depends on which transition metal you use, the oxidation state, the ligands that you have, and even more complex topics like the solvent. So we'll see coming up how this energy gap controls some of the properties of our transition metals.